But there's also, I think, yeah, like uniform.
All right, we should get started. Announcements. We have an exam on Friday. Has anyone looked at the study guide enough to come up with any practice problems that they would like me to look into between now and the exam? Yeah.
It's not super much, but it's our school. Yes. Right.
Context-free pumping lever. Would that be useful to other people as well?
Yes.
I haven't looked at it yet, so, but if there's a Turing machine, that could.
Okay, so, all right, I'll look at some practice
I felt
problems.
really awkward writing, doing the full scan the other night, I was like,
Yeah.
this feels strange having multiple like rules for one thing for a Turing machine system. I don't know, it just
Yeah.
it's more awkward.
It's because they're meant to be deterministic.
Yeah.
They're meant to model a deterministic system. So implementing them as a non-deterministic system does feel weird because determinism is not equal to non-determinism.
Yeah.
Like, there's separate processes. Yeah,
I had some questions in the Turing machine and like the not grammar, the languages essentially.
yeah,
Part, I just have to look them up because I wrote them out.
okay. So yeah, I'm happy to answer any questions at the start of any of the class periods between now and the exam, and especially early this week. I am very much hunting for practice problems that would be of use to people. So we can do anything from the optional homework problems. I can go over other problems in the book. I'll find something to make sure that we have a good understanding, so. So my list is context-free pumping lemma and non-deterministic Turing machines so far. If anyone has anything they'd like to add to that at any point, let me know in person, shoot me an email, and I will come up with something.
I don't know.
I'm also honing in on our second project. It looks like it's going to be implementing the first function, follow function, and LL parse. So we'll start going over that this week. I'm guessing we get to most of this. We'll probably start talking about the first function today, the follow function tomorrow, and then LL parsing either later this week or at the beginning of next week, but it will at least give you something to start implementing. If this is the project you want to choose over CYK, or if you would like the extra credit from implementing both projects.
How much extra credit would we be looking at? For
I have
example?
not figured that out. It would be something like, I don't know, maybe 10 to 20% of the project.
Yeah.
Project grade, so something like 2 to 4%. I don't know if that makes it worth it, but
Yeah.
I don't want to give 20% extra credit for doing it. That would be a little ridiculous.
You're right, we should do very higher.
The second one, the optional one, we're for.
Yeah.
A good way to get everybody to do it.
Yeah.
All right, so last time we looked at some parsing, we looked at an actual syntactic kind of example that looks like it comes from some very rudimentary programming language. So we wrote a context-free grammar using these non-terminals, right? And then we, in addition to the expression, and we came up with something like this. It could be significantly more complicated, but you didn't need more than this to just derive this particular program, at least. Then we went through and did we finish doing a parse tree? I forget if we finished the parse tree or not. Were we working on it? I think we were working on it. So I actually have these animated in the wrong order. So here we have a parse tree. Or sorry, here is the parse, and then from this parse, build a parse tree. Did I start this process? My memory is very faint about this already. No? Let's start there then. So here's a derivation that allows us to, according to the grammar on the previous slide, generate the program that is also on the previous slide. So go ahead and draw out a parse tree for this particular derivation. So remember that parse trees have leaf nodes wherever we have terminals, and they have internal nodes wherever we have non-terminals. We start with a single root node that has the term program. And then we will start deriving from there terminals and non-terminals. So the question is, what here is a terminal and what here is a non-terminal? Well, we know all non-terminals come in those angle brackets, so that should help as well. You can verify your parse tree by attempting to traverse the parse tree and attempt to be able to reconstruct the program. If you do a pre-order traversal or the equivalent of a depth first search, you should be able to reconstruct the exact program. Anyone need access to the program on the prior slide? Does everyone have everything they need from this slide for now? There's the program. And the grammar. Anyone think they have a valid parse tree yet? Couple people, we'll give you a little bit longer.
Kind of unrelated.
Yeah.
When do I have to work for you?
Probably middle of next week.
Okay.
Yeah, I'll assign something middle of this week with the full expectation that people don't start it till after the exam.
Yeah. Like trying to prepare myself for the next like 3 weeks of stuff.
Yeah, that will be the last homework.
But
So we'll have one more homework assigned middle of this week that'll be due middle of next, maybe even end of next week, honestly, if there's no reason to submit it earlier, yeah.
Should this homework be just be graded by?
My goal is to have it graded at least by Wednesday, but that will depend on Harley as usual. All right, I think we have a parse tree. Let's take a look at a parse tree. So we have our program non-terminal coming in, we have main, the open and close parentheses should also be there, but then we have a sequence that is going to be redefined to be we have sequence that is going to be defined as line and sequence. We in the line have an assignment. The assignment is going to be of A and 4. Then we have another sequence broken down into a line and a sequence. That line assigns B to 8. That sequence is a print, which is the expression that is given in, oh my gosh, what's it called? What's it called when the operator comes before the operands?
Oh.
Back to data structures, back to data structures. Yeah, infix notation, thank you. So this doesn't necessarily have to be exactly how you lay out the parse tree. This is how the book lays out a parse tree. The way that I've done it is kind of as an internal node, and then the edges there are either not come to nodes that are non-terminals or terminals. Either way you do this will be fine. As long as I have, again, a way of understanding your parse tree and parsing your parse tree. Exactly what notation you use to produce it is mostly irrelevant, as long as it portrays the same intellectual idea. So that was parsing. So recall that we're going through the steps of the compiler. And so we talked about tokenizing and scanning to produce the tokens. We talked now about parsing. So we're going to move on to what type checking does. The first main goal of the type checker is to look for semantic errors. So we know that parsing can help with syntax errors, and we know that if we're able to derive a parse tree from a given program, we know that the program is syntactically correct in the language of the grammar. But it says nothing about what those lines actually mean and whether those lines are something that we can actually perform. So we thought of doing something like char C equals 6.2. We have a type error there, and again, syntactically, it's perfectly correct. But semantically, it's not something we can actually perform. We can't shove a float into a character variable. So we can now look at our parse tree and see if we can figure out, all right, is this parse tree semantically valid as well? Semantic errors can either be terminating or non-terminating, and whether or not the program can continue with that particular semantic error. What do you think would be an example of a semantic error that would not force the program to terminate? Potentially, depending on the language, if it has a way to recover from that. Yeah, there may be some internal logic. One of them is like double D equals 5. This is something that you're used to being able to do, right? The 5 just becomes 5.0 magically. But remember that if this is a terminal 5, the internal representation of that is going to be as an integer. Luckily, the compiler has a built-in method, program, whatever you want to call it, that converts integer representation to float representation, the equivalent float representation. So you can type a line like double D equals 5, and the compiler will handle that for you. Everything that you've ever taken for granted like that of, oh, I guess that works. That usually means there's something in the compiler that is doing that work for you underneath the hood so that you can be lazy. So a method takes two parameters, an int and a float, and it's passed an int and a string. Is this a terminating semantic error or a non-terminating semantic error? And in which language?
Terminating in Java.
Definitely terminating in Java, right? We can't easily make sure that that string has a particular float representation. What if it's the string 6.2?
Python might. Might not care.
Python might not care.
But
As one of the benefits of actually having an interpreter is you do this line by line rather than as the entire program.
Passing it into the method isn't an issue, but when you try to do an operation on it, yeah.
Right. Right.
So the models.
Yes. So in Java, it's very much a terminating issue. Some semantic errors are allowed, and the compiler has some kind of built-in function for handling them. So if it takes two parameters, an int and a float, and it's passed an int and an int, then it's capable of doing that conversion into an equivalent double. This is mainly because all ints have an equivalent double. This is not true in reverse. Not all doubles have an equivalent int. Unless you want to make some kind of assumption like, all right, take the floor of the double and that is the int, but that's usually unintended behavior. So most compilers will throw an exception there rather than, or find a semantic error with that, rather than continue and assume that you meant the floor of the double that you passed in. So this is what the type checker does. Again, I won't go into too much detail about how this is done, but you have an equivalent top-down and bottom-up process that are both working toward and meeting in the middle. You have expected values or expected variable types, and you have actual variable types. So when you see an expression, you're going to start filling in, like it's maybe you have x plus y, where x is an int and y is a float. Then the expected kind of output from that expression is a float. And if the actual type of the left-hand side of that expression is string, for instance, then you find a type mismatch. But yeah, you'll be doing one part of top-down, looking at the expected values of the expected types of variables, and you'll do a bottom-up of the actual types of variables. And then you'll be matching, is the expected equal to the actual for each variable as it's being assigned. The goal of type checking is to be able to produce intermediate code, and you're going to be parsing the parse tree in kind of a top-down order. In the ability to generate, there's a program that is going to be converting each node of your parse tree into intermediate code. So we're going to walk through the derivation tree, generating intermediate code at each node. That will be the equivalent program in some intermediate language. It's usually still very close to the original language. Note that it is simpler code. This is so that this code can map easily to assembly instructions. Because as we know, assembly instructions, if you have something like an add or a move, they can only take two variables. Or sorry, two registers, right? And you do something, you move what's in one register to another register, or you add the value of two registers together and put it in another register. So you need some way of making sure that all of your expressions, every single line of this intermediate code has at most 3 references that would be registers. So if we tried to do something like sum equals a plus b plus c and sum 2 equals a plus b plus d, and this turns into, this is very similar to the process that we went through in making the algorithm for Chomsky normal form, where we took long grammars and we converted them into equivalent shorter rules. There were more rules, but each of them only had reference to either 2 non-terminals or a single terminal. Here we want to make sure our expressions have at most the left-hand side equals the right-hand side being a something plus something, something minus something, where there are at most 2 references on the right-hand side of the expression. And again, note that it is still the same program, but now we can more easily map this onto assembly instructions. Once we have the intermediate code, we're going to go into the code optimizer. So the intermediate code is going to be based solely on the exact syntax that you wrote in your original program. One thing we might note is that there would exist an equivalent program that would be faster. And oftentimes, it is worth going through very efficient processes to try to figure out what those optimizations are going to be. How can I make your code faster? I don't want to go through some kind of cubic function to do this, but if I can go through something that just linearly looks at something and maybe makes some adjustments on the fly. That's usually worth doing because who knows how many times this code is going to be run. If it's in a loop that runs 100,000 times, then analyzing it once to make it faster for each of those 100,000 times is a process that's very much worth doing. So we're looking for optimizations in the intermediate code. Think about the code on the prior slide. Can this intermediate code on the bottom be optimized?
Yeah. Temp 1 and temp 2 are the same, so you can just assign temp 1 once.
Yes.
Use it twice.
Yes, that's exactly right. So note that we're calculating the same thing, A plus B, twice. It would be much better to calculate it once and then use that end result. But note that, how would that be easier to do in this sum 2? Would you have thought to make that change as you were writing the above code? That's something you would care to try to figure out in your actual coding? Maybe, it depends on who's looking. If it's during an interview, maybe. But in general, we're not trying to optimize to that level while we are writing. But the compiler, as an optimizer, very much has interest in making sure that the code that runs is as fast as possible. So sure enough, we can optimize this code into this. So in general, the code optimizer will do lots of things like this to just trim down on the actual work that's being done. It's actually much more in-depth than this example, but I think this example illustrates really well the kinds of work that it can do. Finally, we need to generate either machine code or assembly, whatever the target output of the compiler is. Machine code or assembly or bytecode are the three big ones. So here we have the line from the optimized code before, temp1 equals A plus B. If we wanted to map this directly onto assembly instructions, we could do something like this. Move what's currently in A into register 1, move what's in B into register 2, add what's in register 1 and register 2, and then move what's in register 2 back into temp1. So we can see how that process at each step is as straightforward as it could be. We don't do two steps at once. We don't optimize and convert to machine code. We optimize one pass and then convert to assembly in one pass, or convert to bytecode, or convert to machine code. Questions on the overall process of compilation? All right, so we're going to look at the last couple components that help us to do this process. So what are the actual data representations as we do this? And then we're going to hone in on the parsing process and learn exactly how that is done in much more detail. So we need a symbol table. A symbol table is a lookup for the compiler, for the program that is running. And it's going to be able to say, if we come up with a particular variable name, we can look at the current value that is stored in that variable in a particular table. And note that these symbol tables are scope specific. So if you redefine a variable in another scope, then the symbol table is only storing the current scope's value of that variable. So there's no confusion between, for instance, a global X and a local X, or an X in another method and an X in yet another method. Or even worse, in C++, you can just start scopes. Has anyone seen this happen? Where you have some method and you can just, at the start of a line, do an open curly brace and suddenly you're in a new scope with no name. You can do something like, I love this language for so many reasons. I'm in C at the moment, but just hang with me. So we have int main, and we have like int x equals 1, Open a new scope. Int x equals 2. Open a new scope. Int x equals 3. Close this scope, or I guess you could print x, print x, print x, and you'd get the local x each time. You just start new scopes without having to name them, without having to do anything. So something like this would be important for the symbol table. There's a symbol table for every scope. So as we scan, we need to recognize identifiers. We need to be able to recognize the current scope that we're in and have the associated logic to be able to store all of that. We call these activation records. Has anyone seen or heard of activation records in prior classes? It's the data that's actually stored on the stack when you have a method call, or you open a new scope of some kind, you add an activation record to the stack, and that contains information like the names of all of the variables, the current values of all of the variables. I would hope that an architecture class would go over that in a bit more detail. So as we parse, we'll also add additional information to this table once we figure out what the associated variable type is going to be. Once we figure out actual values, if it's syntactically correct, we start adding additional information to the symbol table. When we get to type checking to figure out if something is semantically correct, then we'll need to refer back to this symbol table to be able to make the decision about whether it's semantically correct or not. Finally, as we go along, we have error checking. And error checking looks a little bit different in each phase. So as we're scanning, remember we have some kind of DFA representing whether tokens are allowable or not allowable. So we may end up in a non-final state when we're trying to identify a token. And we just come upon some white space. And this doesn't match to a kind of token that we are expecting. So we need some way to throw an error that we found a token that was not the token that we were expecting. When we're parsing, we may find that a group of these tokens don't match a particular grammar production. So we throw yet another kind of syntax error. We either have this is not in the language, this individual token is not in the language, or the sequence of tokens is not in the language. This would be like the green if 6.5, 3.2 from last week. When we do find an error, we need to make sure that the user knows as much about that error as possible. So we'll do some logging and then report that error to the programmer, which is usually what you see when you try to run a program that has a syntax error. Thankfully, most IDEs make this very difficult to do. But in the old days, you would actually see things like you would have to go run your compiler. You would have no syntax highlighting. You would be doing the equivalent of programming in Notepad, or my experience was in Eclipse. There's no syntax highlighting. You go run the compiler program, and the compiler program will tell you where your syntax errors are. So that kind of data logging is done. It's just that an IDE is interpreting that for you. It's interpreting the kinds of errors that it runs. Every single time you type a key, it's running the built-in compiler, and it's looking for syntax errors in what you have typed. It's underlining right where the syntax error says your error is, that is being reported by the compiler. So again, this is still happening. It's just being interpreted for you by the IDE. Same work happening underneath the hood. Questions about either of these components? All right, it's time to dive into parsing at a much deeper level. So a lot of what we've been doing so far this quarter has been preparing us for this. We have the tools now with the addition of a couple other algorithms that we will need for parsing grammars to be able to answer very specific questions about the grammar. We have those functions paired with the grammar for the language, and we have everything we need to actually implement parsing. So let's actually dive into it. So we've looked at this throughout the quarter, right? We looked at parsing with respect to context-free grammars. How would we actually answer things like the membership question? Is this string generatable by this grammar? We came up with a really dumb way to do it. And then we came up with CYK. So we had exhaustive search parsing, where we were just generating anything that the grammar could generate, hoping it would eventually generate our program. Starting with the start non-terminal, we just applied every possible rule that we could to see if we could generate the target program in any number of steps. If there were multiple productions for a particular left-hand side non-terminal, so we'd have A arrow one definition or one right-hand side, A arrow another right-hand side, what did we have to do? Try both, right? Kind of treat it either like a depth first search, but your depth first search may never end, so you probably want it more like a breadth first search, where you make one move in the associated rule, one move in the next associated rule, two moves in this, two moves in that, except that you may end up with A splitting into two possibilities, and then B splits into three possibilities, and then we loop back to A, in which case the depth first search is never going to end. So exhaustive search is a huge pain. Do we remember the complexity of exhaustive searching? Yeah, that's a good answer. It was exponential. It was exponential with respect to the number of productions basically in the grammar. That was your base, and the length of the target output was the exponent, and that just ended up being way too much. So we talked about CYK, but we're also going to start talking about LL parsing. We looked at this very, very briefly for a slide or two, and I said, we'll come back to this. And we're now going to start doing the preliminaries to be able to do LL parsing. So the goal will be that later this week or next week, we're going to look at how this is actually done by compilers. How is parsing actually done? First, we need to talk about, in general, there are two different ways that we can approach parsing in the big picture. The first one is top down. This is what we have done all quarter. You start with the start non-terminal, and then you replace right-hand side non-terminals from left to right. So you find some non-terminal and you go through and you replace it. Both exhaustive and LL parsing are top-down approaches. So LL will pair very nicely to the exhaustive search that we've done, but it's significantly more efficient. There's also bottom-up parsing. In bottom-up parsing, instead of starting with the start non-terminal, we're going to start at the leaves. We're going to start with the string that we're going to generate, and then start to match terminals in the string with non-terminals, with productions in the grammar, and try to derive the start symbol. We can derive the start symbol, then we have the path down to the leaves. There's another kind of parsing called LR parsing that is a bottom-up approach. And my goal is to cover all of these by the end of the quarter. I think we can do it. Questions about top-down or bottom-up parsing? How that would look, how that will work? We'll get a couple examples here in a moment, but I'd like to clarify any questions you have? All right, we have a grammar. We want a leftmost derivation and a parse tree. Let's say we're trying to generate, we need a string, don't we? Just a second, I'll get the string for you. AABCBC is the string we need. Should be.
Need another B after the A. After the second.
Let's go through it step by step. I think this works. So we start with S to A, capital B, lowercase c. This A splits into AA. Then we replace that A with B. Taking the B, we can then split that into B, capital B, B. And that B can become a C. There's one more B, AABBCBC. I made a mistake. Good point, good catch. There needs to be a second B there. So this is top down because we're starting from S, and then we're redefining every leftmost non-terminal as we see them in depth first search order. So we expand the A, now come back and expand the B, expand the B, and then we have a depth first search string. So let's do the exact same thing for the exact same string, but let's try to do a bottom-up parse. So now start with the string and see if you can generate a bottom-up parse from this. So to start, we're going to look at this string and try to map some of these to the left-hand side of some of these. And see if we can derive the start symbol. So if we look at this, what do we see that maps to something in here? Where should we even start? What do we see? You be funny. Take a
The start symbol always has an A on the left. Can we like? Well, I don't know, the bottom of, at least the description you gave said you start from left to right,
Yes.
so.
Well, we want to be able to map it with a single rule. Yeah, so we don't have a capital A or a capital B to map here. So we have to find something that we can immediately map.
Okay, the first B could be a capital A then.
First B could be a capital A. So you want to say something like this becomes capital A.
Yeah.
Then what could we do?
Then the A, capital A could be an A.
This A, capital A is an A. Excellent. What comes next?
Probably the C becomes a capital B.
This C becomes a capital B. What comes next? B capital B, B, that can also be defined as a B, so we'll take this and this and this and bring them together and make a B. So now we have A, capital B, lowercase c, which is what we have as our start symbol. So we can now take this and this and this and this and define that as S. Since we were able to derive the start non-terminal from this via a sequence of kind of collapsing the string on itself by applying the rules in reverse, we're able to find the parse. And this is kind of bottom up, exactly what we did here. We're taking the lowest things here and we're just slowly collapsing until we can't collapse anymore.
It seems pretty efficient.
There is. both top-down and bottom-up parsing are efficient, assuming we have some other algorithms in our back pocket, which is what we're gonna be talking about momentarily. We're gonna talk about the algorithms that make this process efficient. Questions about bottom-up parsing? So we start here, continue work, and eventually just get here. Which I think is exactly what I do. And note that we are able to get here directly from a rightmost derivation. So if you construct this rightmost derivation, where we're going to be expanding the rightmost non-terminal, so we apply the S, and then we expand the B, and then we expand that B, and then we expand the A, and then we expand the A again to derive the string. This process, exactly in reverse, tells us how to do the bottom-up parse. Okay, with 8 minutes to go, make sure you have your caffeine. We're going to dive into the 2 algorithms that we're going to need in our back pocket to be able to implement LL and LR parsing. The first one we're going to care about is called the first function. We'll note that the reason that the silly derivations were so inefficient is that we had multiple applicable rules that we could use at one point. And we need some way of reducing that search space because we cannot be looking at multiple things at a time. We just can't if we want to be efficient. So we need some way to make this decision efficiently. So 2 functions, they're both going to be used in LL and LR parsing. The first is called the first function and the second is called the follow function. And the follow function uses the first function. So we're going to start with just the first function. Given a context-free grammar, the output to the first function is just the possible set of terminals that could that could be the first terminal of a particular derived string. So we have something like A arrow something. The question is what terminal in some string could be there? If we're in the alphabet ABC, maybe A could follow or C could follow, but not B. That's very useful to know. Because if we had 2 competing rules, A arrow something and A arrow something, and one of them tried to generate something that we didn't want, we could ignore it. So we need to define the first for every non-terminal. And we can start with the easy question. The first for each terminal is just the set including itself. So the first of lowercase a is the set that contains A. The first of lowercase b is the set that contains B, etc. And the first of a non-terminal will start as the empty set, and we will continue to add to it as we explore the grammar. We will start with the first of a particular left-hand side, and then to define that, it will be defined to be the union of the first of every production in the right-hand side. Finally, I'm going back and forth with the capitalization of this. I apologize. They should all be capitalized. The first of a given production is the first of the first symbol in the right-hand side of the production. Let's take a look algorithmically, and then we're going to get some examples, because I think just defining the rules doesn't really help you see what this is going to do. But I think that, so here's the algorithm. Consists of 5 steps. So for every terminal in the grammar, the first of that terminal is the set that contains itself. One other point that's here is the first of lambda is just the set that contains lambda. We can count lambda kind of as a terminal, the empty string. So it counts under that same rule as the first as a terminal. For every non-terminal, The first of that non-terminal starts out as the empty set. And then we go into a loop. Repeating until there are no more terminals or lambda can be added to any of the set of first for the non-terminals. We're going to iterate through every production that is some non-terminal arrow something. And this W could be any list of terminals or non-terminals. So the first of A is now going to be defined to be itself union the first of this production. This right-hand side, W, whatever it happens to be. So you're gonna loop that process. It isn't gonna give us any information until we're able to answer step 5 about a complex right-hand side. So W is made up of a bunch of symbols, either terminals or non-terminals, and we're going to label them X sub 1, X sub 2, X sub 3. So maybe X sub 1 is a non-terminal, X sub 2 is a terminal, X sub 3 is a non-terminal. Does not matter. We just need to figure out what the first of that sequence is going to be. So the first of the entire string is going to be the first of the first symbol in that right-hand side, but can't be lambda. So if that could contain lambda, we will remove lambda from the first. Then for every following symbol in that, you need to look for lambda. If lambda is the case, then you may need to start exploring the first of that character. So like, let's say we had some A arrow B C. And then we had a second rule, B arrow lambda. We want the first of A to be the first of A union the first of B, but the first of B is lambda, and we can't have lambda in this. So the first of B is now, in this case, the first of this production is now just the terminal C, because B goes straight to lambda and lambda can't be part of the first function. So we only need to look at the second character and later if something maps directly to lambda. Does that make sense? We'll get some examples of this. We have just a couple of minutes, so we'll do the easy example and save the more difficult example for tomorrow. Okay, so we need to calculate first of the start non-terminal for the following grammar. And to do so, we'll need to calculate first of the rest of it, but fairly simple grammar. But how would we do this? What is the first of everything that is here? The easier one to see is the first of capital A. So I guess, I don't know, let's first do the first of we want each terminal. All right, we know that's true for each terminal. There's no lambda anywhere in this, so we don't need to worry about lambda for now. But how do we calculate first of capital A? What is that? So by the rules in the prior slide, first of this is the first of each place that it could go. So B and C, I'm going to write this as I'm going to write it like that. So that helps us, right? This is a definition for first A. It's the set BC. So now what is first S? It's the first character of each of these. So we have. First A union. First capital A. We've now defined first capital A as the set BC. So we can say that this is the set A, B, C. And this tells us if we see an S, it is possible for a string that starts at that non-terminal to start with either A or B or C. We can derive rules for strings that start with any of these three letters.
Does every string in this language start with A though?
Not necessarily. S to capital A to lowercase b, S to capital A to C. We have ways that we can generate strings that can start with any of these three letters. So this is the process that goes through and answers that question. But we also have first and A. If we start with the subproblem that is we're at A, we can only generate strings from here that start with B or C. We can no longer be at A and generate strings that start with A. So that's the purpose of the first function. We'll come back tomorrow, recap this, and figure out how in the world we're going to handle lambdas. Well, I'll see you for that tomorrow.